Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, the periodic table. Today we will begin with lecture 9 from the course, but make sure you have watched the previous ones before viewing this one. So in the last lecture, we started the discussion on the periodic trends in properties of elements, wherein we learned about what is atomic radius and the types of atomic radius. So we will continue that discussion further and see what are the factors affecting atomic radii and then the general trends about these atomic radii in the various periods and groups. So we will start the lecture with the factors affecting atomic radius. But before I tell you what are these factors, let me make one thing very clear to you. All these factors, they are not going to affect the atomic radius singly. There is going to be a cumulative effect of all these factors that we are going to study. We are going to study 4 of them, and all of them, they are going to have a cumulative effect on the atomic radius. Please always do remember this. So the first factor we have is the number of orbits. So number of orbits you can understand from the definition of the atomic radius itself. What is atomic radius? Well, it is the distance from the center of the nucleus to the outermost shell of electrons. So if there is an increase in the number of shells or the orbits, the atomic size is going to increase. But again, do remember that it is not going to be the single cause for increase in atomic size. We have to see the nutshell of all the factors which are affecting the atomic radius. So the second factor we have is the nuclear charge. So increase in nuclear charge, this makes the atom smaller. Why? Because nuclear charge means the number of protons. So number of protons is increasing. This means that the nuclear charge is increasing, and nuclear charge is increasing, meaning that the attraction towards the electrons, that is increasing. The electrons are going to be pulled closer to the nucleus, making the atom smaller. And the third we have is the shielding effect. So shielding effect we have discussed quite in detail while we were discussing the lecture on shielding effect. So I hope I do not have to repeat all that again. And more is going to be the shielding by the inner electrons. More is going to be the atomic size, because the electrons, they are less attracted towards the nucleus. Right? So you can see from here also something increasing the atomic size, something decreasing the atomic size, and we will have a cumulative effect of all these factors. And then we have finally the bond multiplicity. So bond multiplicity, what do we mean by that? Bond multiplicity is the number of bonds between the two atoms. So that can be a single bond, a double bond, a triple bond, and more is going to be the number of bonds, smaller is going to be the atomic size. So I hope all these factors, they are clear to you, and when we are discussing the trends about these atomic radii in the period and groups, all these factors are going to be important. So now let us understand what are these trends in the periodic table. So we will be discussing the period first of all. So now in the period, what happens is the atomic radii, they decrease as we move from left to right in a period. And how do we understand this? Let us go back to the factors. So first is the number of orbits. Number of orbit, is it going to increase in a period? No, it is not. The electrons, they add to the same valence shell when we move from left to right in a period. So no new shell is being added. The electrons are being added into the same valence shell. So this is not going to affect the atomic size, right? So the next thing that comes is nuclear charge. Is the nuclear charge increasing? Yes. With the increase in atomic number, the nuclear charge is increasing. Next, we come up to the shielding effect. So shielding effect, is that increasing? Well, there is an increase in shielding effect, but the valence electrons, they do not contribute much to the shielding effect. So the increase is not much. So as a nutshell of both these factors, the effective nuclear charge increases. So the effective nuclear charge is increasing, no new shell is being added. So the net total of this is going to be a decrease in the atomic size. Okay, which you can see from the this table also, that we have the period 2 elements atomic radius and period 3 atomic radius. So the all from lithium to fluorine, you are seeing that there is a decrease in the atomic size, and then from sodium to chlorine also you can see that there is a decrease in the atomic radius, which is even visible from this graph. For lithium to fluorine, you are seeing that the atomic radius is decreasing with increase in atomic number. Well, you will be thinking why we have not added neon to this chart, right? Or for that matter, we have not added even argon to period 3. Well, that is because for the noble gases, we consider the van der Waals radius, and these are the covalent radius. So always the van der Waals radius that is going to be greater than the covalent radius. So that is not been added. We do not have a covalent radius for the noble gases. So next we will be discussing about the group trends. So in a group, the atomic radii, they increase as we go from top to bottom. And why is it so? Again, see the factors again. What about the orbit? Well, with each added member, a new orbit is going to be added. For example, in the group 1 elements, lithium is going to be 2s1, sodium is going to be 3s1, potassium 4s1, and so on. So a new orbit is being added. This means that the atomic size is going to increase. What about the nuclear charge? Well, obviously the atomic number is also increasing down the group, so the nuclear charge is increasing, and this is going to contribute to a decrease in atomic size. What about the screening effect? Because a new orbit is being added every time with a new member, so this means that the number of inner shell electrons is increasing, and if the inner shell electrons, they are increasing, this means there are more electronic repulsions, and there is going to be more value of the shielding constant, and hence the outer electrons, they are attracted towards the nucleus to a lesser extent. And the sum total of all this is going to cause the increase in the atomic radius down the group. This you can see with the values of the group 1 elements and the group 17 elements as well. From lithium to cesium, you are seeing there is an increase in atomic size. For group 17 also, from fluorine to astatine, you are seeing there is an increase in atomic size. So what do we have in a group? Increase in atomic size. Again, you can have the graph for the group 1 elements also to see the increase in atomic size. Now, there are certain facts that you have to remember from this discussion of the atomic radii in periods and groups is that for the same period, the alkali metals, they are going to have the largest atomic size. Even you can see from comparing from lithium to fluorine, lithium having a radius of 152 picometer and fluorine having 64. So there is the largest size of that being the alkali metals. Okay, similar you can see all comparing the group 1 and group 17, you can see the alkali metals, they are going to have the largest atomic size in the period, and halogens, they are going to have the smallest atomic size. What about the noble gases? Well, noble gases, they are going to have a large size because we are taking the van der Waals radius in case for noble gases. Okay, so I hope everything is clear to you till now. So let us see a few exceptions to the general trend that we have learnt till now. So group 13 elements, what do you expect? We expect that going from top to bottom, there is going to be an increase in atomic size from boron to aluminium to gallium to indium and thallium. But well, this does not happen actually. The observed trend is that boron, yes, this is the smallest size, but then aluminium and gallium, they are almost similar in size. Gallium is not having atomic size larger than aluminium. Why is it so? Let us see again our factors. First factor was the number of orbits. From aluminium to gallium, there is increase in the number of shell. What about the nuclear charge? Yes, this is increasing. So till now, what all we have discussed for the normal trends, this is happening. The change comes in the shielding effect. Why the change? Because now in the inner shells we have the 3D electrons in case of gallium. So these 3D electrons, they are going to provide a poor shielding effect. So the value of the shielding constant, that is going to decrease, right? So if this is going to decrease, what will happen is that the effective nuclear charge will increase. Effective nuclear charge increases, so this is going to cause a decrease in the size. So this is going to more than compensate the increase in size because of the number of shells, and hence we have aluminium and gallium almost similar in size. I hope this is clear, that this is because of the poor shielding by 3D electrons that the gallium has size similar to that of aluminium. The next trend is going to be for the group 3 and 4 elements. What is that? Let us see. We have group 3 elements to be scandium, yttrium, lanthanum and actinium. Right? So what do you see over here is that scandium, this is going to have size smaller than yttrium and smaller than lanthanum and smaller than actinium, so which is as expected. Okay, this is expected, this is what we observe as well. What happens in group 4 elements? What are you going to expect? We are expecting that down the group the atomic size is going to increase, right? So titanium will have smallest size, then zirconium and then hafnium. But what we see is that the size of zirconium and hafnium, this is almost similar. Why is it so? So if you understand the 4D and the 5D series, they are going to have similar size, that is zirconium and hafnium, they will have similar size because in them there have come the 4f electrons, and these 4f electrons now, they are going to provide a poor shielding effect, and hence they are going to cause an increase in the effective nuclear charge. So whatever was the increase in size because of the increase in number of shells, that has been compensated by the increase in effective nuclear charge. Okay, so there is a gradual decrease from zirconium to hafnium, and this is called as lanthanide contraction, and similar trend we see in the whole of the lanthanide series. There is a gradual decrease in the lanthanide series because of the poor shielding effect of the 4f electrons, and this is termed as lanthanoid contraction. Okay, so down the group also and throughout the lanthanoid series, there is a gradual decrease in size, and this is called as lanthanoid contraction. So next trend that we have to discuss, and in fact we have been discussing, is about the noble gases. Right? So noble gases, we consider the van der Waals radius. So if we consider the van der Waals radius for all the period elements, okay, for example, we are considering the period 2 elements from lithium to neon. If we consider the van der Waals radius for all of them, lithium is going to have the largest radius and neon will have the smallest radius, right? So this will be in accordance with the expected trend that in a period the atomic size decreases. But when we consider the van der Waals radius for neon, because for this we can consider only van der Waals radius, and for the rest of the elements we consider the covalent radius, then what is going to be the order of atomic radii? Neon is going to have the largest size because van der Waals radius, this is larger than the covalent radius, and for the rest of the elements lithium is going to be the largest radius going up to fluorine. So I hope this is clear that what is going to be the order when we consider van der Waals radius and what is going to be the order when we are considering the covalent radius for group 1 to group 17 elements. Okay. So the next important trend we have to see is the transition elements. So if we consider these 3D elements, from scandium going up to zinc, what do we see? We do not see a constant decrease in atomic size. Why is that so? Let us understand. From scandium to chromium, what we see is that the atomic size decreases. Then from manganese to nickel, the size remains almost constant. And then from copper to zinc, the size is increasing. Well, why is it so? Let us again understand in the terms of the shielding effect and the effective nuclear charge, because the electrons, they are being added into not the valence shell, they are being added into the n-1 shell, the penultimate shell, right? So here from scandium to chromium, what do you see? We are seeing that the shielding effect, this is going to be less than the effective nuclear charge, because the electron repulsions in these elements, they are not significant, as there is no pairing of electrons in the d orbitals, right? And then when we move from manganese up till nickel, what is happening? They're going to be starting the pairing of electrons, and when there is going to be pairing of electrons, the electron repulsions, they are going to increase, and the shielding effect value, these balance the effective nuclear charge, which is due to the increase in the nuclear charge. Okay, so here these values, they become constant, and then from copper to zinc, the number of electronic repulsions, they have increased. So we see that the shielding effect values, they more than counterbalance the So that would be all for this lecture. I hope you will join me back again for the next lecture, which is going to be very important, where we are going to discuss the factors on which the atomic radii depend, and then we will be seeing the trends of atomic radii in the periods and groups. So if you have any doubt in this lecture, please feel free to mail me at h2ochemistry@gmail.com. Also, you can put any of your doubts in the comment section. Do subscribe to our channel H2O and click on the bell icon as well to get a notification as and when we put up a new lecture for you, a new course for you. And if you've liked the lecture, please do give an appreciation by clicking on the like link. Thank you. See you again for the next lecture. Have a nice day. God bless you.